Okay, so this is part two with global climates and biomes. And just like on land and in our atmosphere, ocean currents are driven by physical factors, temperature, gravity, differences in salinity, overall density, prevailing winds on the Earth's surface, and the Coriolis effect. As well, these ocean currents bump into the continents, and so the actual shape and boundaries of the continents themselves and the continental shelves dictate the motion of a lot of these currents. So, warm water, just like air in the atmosphere, expands and rises, and cold air sinks. Cold water sinks. And so we have the formation of these large-scale ocean-wide gyres, which are basically currents that operate in a circular motion. And in the northern hemisphere, they tend to be, operating in a clockwise manner, and in the southern hemisphere, counterclockwise manner. And there are basically 5 gyres. Mr. Rogers is close friends with a person who is in the leadership of a group called 5 gyres. And they travel the world's oceans and look specifically at plastic pollution that tends to accumulate in the center of these gyres due to the circular motion of the currents. And they are working on developing technologies to remove that plastic and just promoting awareness about plastic pollution in general. Okay, so these gyres are also connected. They're not operating totally in isolation from each other, and we'll see that things like upwelling help connect these gyres. So upwelling is just basically vertical motion within the water column, and graphically, as you have surface winds pushing on water, they tend to push water in some cases away from the continent itself, and that allows for colder water from the deep ocean to come up to the surface, and that often brings a significant amount of nutrients, carbon, nitrogen, phosphorus, nutrients that are needed for primary production and photosynthesis. So where you have a significant amount of upwelling along the coast, you tend to have high levels of primary production or photosynthetic activity as well. Okay, so we said these gyres are connected, and the term is, you'll alternately hear global ocean conveyor or thermohaline circulation. Thermo meaning temperature, and haline meaning salt. And so this global ocean conveyor or thermohaline circulation is moving throughout the world's ocean basins in a long, and very dynamic and robust current, bringing warm water to polar regions and colder polar water to more equatorial regions. And the cold water tends to flow along the bottom of the ocean, while the warm currents tend to be closer to the surface. And thermohaline circulation serves to distribute heat from equatorial regions to the poles, and work towards creating an equilibrium condition, although it's constantly being disrupted by incoming solar radiation. Okay, so heat transport. With that global ocean conveyor, there's a tremendous amount of heat being transported in those warm ocean currents. And we know that water has a significantly higher heat capacity than air. And so when you heat a water mass, it takes a long time for that water mass to cool. And that water mass can actually radiate heat to the atmosphere in a significant way. And so consequently, places that are on the receiving end of, say, the Gulf Stream, such as Great Britain, can be significantly warmer than areas of the same latitude, but that aren't receiving that heat directly. And so you look at the Gulf Stream here, transporting warm water directly over to England and into the Baltic Sea here. And even in southern Sweden, where my family lives, they have exceptionally warm ocean there. And that's because they're receiving warm water surface waters that have been heated in the equatorial Atlantic and delivered rapidly to northern Europe. Okay, another aspect of this is the idea of this oscillation that occurs. Oscillation is essentially flipping back and forth between two states. And so in the Pacific Ocean, there's this condition where equatorial winds, trade winds, may blow toward the coast of South America and pile warm water along the coast, or away from the coast of South America and toward the west, and bring warm surface water away from the equatorial coast of South America. And so these two states are the El Nino-La Nina phenomenon. And when you look at that, when you have an El Nino condition, again, you have a large amount of water that's warmer than average, piling up against the coast of South America. And the reverse, the La Nina or normal condition, you tend to have that warm water piling up in the Western Pacific. Okay, so there you can see, in a heat map, large amount of warm water at the surface of the, Eastern Pacific Ocean. And what that means is, when you look at the relationships or how that drives global climate patterns, here in California, and especially in Southern California, we tend to have an El Nino condition. We tend to have wet winters, and the entire southeastern portion of the United States tends to be relatively wet and cold. And then conversely, in the coastal regions, British Columbia up into Alaska, they tend to be warmer than average during an El Nino condition. La Nina, you can see, is the other side of the oscillation. So if this is warmer than average surface water in the ocean, La Nina is colder than average water in the Eastern Pacific. And you can look at that. We have a series of instruments that measure the deep ocean as well. And you can see this warmer than average water descending below the surface during an El Nino condition. And this is measured carefully by satellites and Argo floats that are deployed in the world's oceans. And it appears this year that we're oscillating toward a La Nina condition, which would tend to lead to a drier winter for us. So we'll see if that holds true. Okay, and one of the final concepts is this idea of rain shadows and driving biome formation. So as we live in California with a series of mountain ranges moving, as you move away from the coast, we have a number of different rain shadows, really all along the west coast of the United States. And what happens is, as these air masses come in off the Pacific Ocean, or really off of any ocean, they're carrying a fair amount of moisture and water vapor. And when they hit these land masses, these mountain ranges, those air masses are forced to rise, gain elevation or altitude. And as they do that, we have this adiabatic cooling phenomenon that happens, and those air masses can no longer handle or hold as much moisture. And so lots of precipitation in California on the western slope of mountain ranges. And then as you move over the mountains, because the adiabatic cooling has effectively, it's like wringing a sponge, just remove the moisture from the atmosphere. The leeward side, or the eastern side of the mountains, tends to be what's called a rain shadow, or significantly less precipitation. And, as we see in California, we transition into the desert environment pretty quickly on the eastern side of our mountain ranges. So again, the way this looks graphically, warm, moist air coming in off the ocean rises, and you get a lot of precipitation as it cools off. And then as that air mass moves over the crest of the mountain range and descends on the other side, you have warming adiabatic heating and relatively little precipitation. So this would be the rain shadow side. Excuse me. Another graphic here showing lots of precipitation on the west slope of California's mountains and dry conditions on the east side. Okay, so all these things that we discussed really determine global biomes, and the variations in the climate regime, precipitation, temperature, predominantly, drive the kinds of plants that you're going to see in a region. And so you look, here again, you have polar zones, relatively colder zones, moderate temperate regions, subtropical zones, and tropical zones. And of course, tropical zones tend to be the warmest near the equator. And so you get a distribution of different biome types associated with those climate regimes. And really the rest of the chapter is a survey of the various different biomes on Earth. And I'll let you look at those. They are defined by, as we just discussed, primarily when precipitation falls during the course of the year, how much, and what are the general temperatures.